On the board, there are three primary equations. Well, there's six, but there's three. There's just two different versions of them, one for degree, one for radians. If you have a calculator, I'd like you to pull it out at this time. We're going to verify these equations actually work and exist. The reason being, well, this is a standard concept from geometry that needs to cross over and its main use. Because it turns out in geometry, this concept was like one of those, cool, and then forget about it. In Trig, this has a lot of extra uses that are really powerful. So we're going to stick with the first two. The third one is also true, but not as useful. What it states is that sine and cosine are related to each other via a simple complementary angle. So in other words, if you know an angle that you want to be for sine, there's a simple way to convert that angle to make it work for cosine instead and get the same result. Think about it this way. Sine is based upon very specific sides and angles of a right triangle. Cosine is based upon slightly different ones. Those two components, if I have a different angle, end up matching up. So here's how this works. You got a calculator? Type in the following. Sine of 21 degrees. Now it's in degrees, so we're going to use the degree version of the sine formula, which states sine of theta is equal to cosine of 90 degrees minus the angle in question, so minus that 21 degrees. If you got a calculator, I want you to first type in sine of 21. Okay. Sine of 21 as a decimal, please.
It is 0.358.
Okay. Take a seat, Anna. Let's go. Come on. And, other side. Equals. Now, on the right-hand side, it's going to have a different angle because it's a different trig function, but will lead to the same result, 0.358. Cosine, instead of being for 21, we're going to use instead cosine of 69 degrees.
Yeah.
Turns out cosine of 69 degrees is the same value as sine of 21 degrees. This is because mathematically they are called complementary angles. They have this natural relationship. And this is actually pretty easy to prove in terms of a picture. So what I'm going to do now, let's pull up the picture version of this. So I'm going to have an unnamed angle, which I'm going to call theta. We got a right angle down here. And I'm going to give my sides, I'm going to call them the opposite side. Or in this case, I'm going to use the old notation, A, B, and C. Okay, so if I wanted to talk about sine. Sine of theta, in this case, would be equal to the opposite of theta, which in this case would be A over B. Oh, sorry, A over C. If I was to instead look at this other angle up here, which I'm going to call phi, if I wanted to use A and C as well, I couldn't use sine anymore because I'm dealing with a different angle. I'd have to use a different trig function because it's a different angle in a different position. If I wanted to look at A and C of phi, I'd have to use cosine of phi. Because it's a different angle, it requires different positions and a different trig function to get cosine to work instead of sine to work. But it turns out theta and phi are complements.
Is that a T?
Yes. Cotangent, contingent? Yes. These are designed to be complements of each other. So in other words, if you have a problem where the angle is not working out properly for whatever reason, or the trig function isn't working out properly, you can always convert it. This is also visible on the unit circle. It's easiest in this first quadrant to see, but it does work for other ones as well. The sine value is equivalent to 90 minus the angle. So look over here. At 30 degrees, remember the sine value number is the second number, so that'd be 1/2. But if I take 90 minus 30, I would get 60 degrees. The cosine value is 1/2 at 60 degrees. So these two have the same value, despite being in different positions and looking at a different trigonometric function. One deals with sine, and deals with cosine, yet they have the same result. It is because they are complements. 30 and 60 add 90, so 30 and 60 will have the same result, one with sine, one with cosine. This always works. I can make a more extreme angle version. Let's say instead of 20, I made this into something like 5. Well, then sine of 5 would be equal to cosine of 85. because they are complements. They add together to be 90 degrees. This is always the case. This is the definition of a complement. Now, your homework question will ask this in a very unique way. That's why I wanted to point this out. The homework questions tonight, at least a couple of them, will say something like, hey, cosine of 41 degrees is equivalent to sine of what? They don't say to come out and use these formulas, but you're supposed to. That's the idea, is to see the connection between the two different functions. This time in the case on cosine, I would use the second set of functions, which states that cosine of theta is equal to sine of 90 minus theta. So I come over here and do 90 minus 41 degrees. And so I get a solution of sine of 49 degrees. And this would be my solution. So cosine of 41 degrees is equivalent to sine of 49 degrees. Because again, they are complements of each other. It's a natural relationship that they always hold together. This works for sine and cosine, or cosine and sine. This also works for tangent and cotangent. And it's not listed up here. There is a similar relationship for cosecant and secant, and secant and cosecant. They always have the same relationship. In other words, there's always a connection between the two trig functions. So if you don't like one, you can always convert it to the other. It just takes some effort. In this case, that's the formula. You may always convert sine into cosine. You just got to adjust the angle. You always convert cosine into sine. You just have to adjust the angle. This is a little bit tougher when it's in radians, so you may want to convert them into decimals, if that's the case. Convert the radian into a decimal value, and then do the subtraction part of it. Of course, if your calculator is good enough or you're good enough, you can do the fraction version too. Doesn't change anything. Example, if I came up here and said tangent of pi over 10 is equal to cotangent of something, well, that something would just be pi over 2 minus pi over 10, whatever that happens to be. In this case, that would end up being pi over 10. Well, I would probably do 2 pi over 5. So tangent of pi over 10 is equivalent to cotangent of 2 pi over 5. And that's the other option, is if you have difficulty with working with the radian one, then convert it to the degree one. And the degree formula works the exact same way. Do you note these are the exact same formulas because pi over 2 is equivalent to 90.
Wait, I just keep getting a decimal.
Which is fine. Then you just put the decimal there instead. Okay. Now, this is a small piece of your homework assignment. The larger piece of your homework assignment involves undrawn triangle trigonometry. These problems are the exact same as last time's problems, like the second set of last time's problems. There's no difference in the math. The main difference, though, is that instead of having a picture where they tell you where the components are, they list the components in a list instead, which adds a level of difficulty because you have to put your own picture together with what is given. To assist with this, I want to talk about the standard trigonometric picture. This is a picture you can always use for every single problem from this point on. However, for certain problems, you may want to make adjustments to it, and you don't have to use this form. But here's the standard trigonometric picture. The standard trigonometric picture has a flat side on the bottom, a flat side going up. There's two different versions of it. This way and its flipped version work the same basic way. Jesus. Colored fonts.
Both can nice things.
Now, there's a lot of different versions of this. Really, the big thing about this is the location of the three different components. That's the big one. If you have these locations correct, it does not matter how you draw this, as long as these pieces are there. So, the three angles are referred to by three capital letters, A, B, and C. The right angle is always the C. The three sides are referred to by a single letter each. They're referred to as the same letter as their opposite angle, just lowercase. So if this angle is big A, this side over here that is opposite it is called little a. If this angle up here is big B, this side down here is little b. If this angle over here is big C, this side over there is little c. Make it clear, one's bigger than the other. Now, this is the standard form of every trigonometric picture, not the standard orientation. You could draw this exact same version of this picture going this way instead. C is going to be your right angle. So that means little c is going to be your hypotenuse. Big A is going to be one of the other two, which means little a is the side opposite it. Big B is going to be the other angle, and little b is going to be the one opposite it. It'll always have this form, this relationship. Big C is always in the same spot, little c is always across from it. Big A is one of the angles, big B is the other angle. And again, you can orient this in a bunch of different ways. It doesn't change the fact that this is going to work out in terms of the trig. If I throw numbers up here, the trig part of this doesn't change. Because if I pick A as the angle, then as long as the correct side is opposite of A, then sine will work. As long as big A is in the right spot and little a is across from it, then cosine of A will work. That's how it's designed.
I need Kelly's mess to the office for checkout. Also the
Big C,
Sam Barton
C,
to the office.
big A, big B, little b. It does not matter the orientation of them. What matters is that you have, first of all, big C in the correct spots, and then everything is opposite of its counterpart. Big A, the angle, is opposite little a, the side. Big B, the angle, is opposite little b, the side. The reason I bring this up, 3 problems tonight, they list all your components in a list where they have not given a picture whatsoever. That does not change the difficulty of the problem, does not change the process we're going to go through. It's going to feel exactly what it felt like yesterday going through some of those problems. The big difference will be you'll have to draw your own picture first and label your sides appropriately. That does not change the type of quality of work we're doing. Let's take a look. Example. I tell you that little c is equal to 158 meters. And angle A is equal to 25 degrees. And I tell you the following set of instructions. Find all missing sides and angles. Very nice, man. Let's go ahead and take a look at the picture first. But you are correct. The missing angle will be 65. So, for these problems, the first step is going to be to take one of those pictures we showed earlier with everything in standard position. Remember, C is the right angle. Little big A is one of these angles. Big B is one of the angles. Little a is across from big A. Little b is across from big B. Little c is across from big C. That's standard position. You can't mess up the orientation. You can draw it whatever way you want as long as those 3 things are true. And then you put these 2 pieces where they belong, and suddenly it will start to look like last time's problems.
Today is Miss Reel's birthday. Everybody be sure to wish her a happy birthday.
Rude. Is Miss Pacheco's birthday too? I bet she's angry right now. Which brings a small smile to my face. What's it? That's up. Now you might be thinking to yourself, Douglas, which one's C? Well, C is guaranteed to be the hypotenuse because of how it's always set up. You might be thinking to yourself, but Mr. Douglas,
I think to myself a lot.
which one's A? I think to myself. Sometimes, Mimi, you need expert advice, so I always think to myself. Ouch. All right. A friend of mine that was in a mental hospital, that was his joke. It's a quality joke. You might be thinking to yourself, hey, where's little a, or angle A is supposed to go? Which one's angle A? Make it look appropriate. Okay? You should always make one of the angles smaller than the others. So, if 25 is a smaller angle, put it in a smaller angle spot. If it's a bigger angle, put it in the bigger angle spot. Okay? But if you mess up, as long as you label everything appropriately, it does not matter. Here's what I mean. Let's say I come over here, I'm like, you know what? This is A. When I set up the trig part of this to actually get to my other 3 solutions, I will find them with this angle right there. I will set them up and find the right trig functions. If I change A to be the top right corner, it'll change the location of my opposite side. It'll change the location of my adjacent side. But as it turns out, the math won't change at all. Because your sides will still be fixed. You'll still have the same problems. Everything will still work itself out. You'll get the same solutions. It does not change anything. So these start to look a lot like last time. Last time, the only difference being we usually had angles and sides labeled like A, B, maybe like phi. Now it starts to look a lot like last time. We're trying to find the missing sides. Okay? Now, Zach, you were 100% correct. Thank you. What did you say about that angle up here?
65.
How'd you get that?
Added 45 and, or, you have to get to 180, so I'm going to subtract 105 from 180.
You are correct. There's a factoid from geometry that's really helpful there. Do you remember what that's called? It's got a very fancy name. It's called
115 from 180, not 105.
It is called the triangle angle sum theorem.
Did you?
Oh, I hated that. Don't
Just not.
Triangle angle sum theorem?
Yeah.
Don't the angles have to add up to a certain number?
Yes, they do. So in this case, I'm going to use this picture. So I'm going to say angle A plus angle B plus angle C has to equal 180.
This is for you. This is for
I'll be sure to let them know that you miss him.
I love Mr. Ford.
I like
Now,
Mr. Forbes as a teacher, but I did not like theorems.
I understand.
I don't think.
There's also, in case you didn't know, because you didn't deal with radians in geometry, fun fact, there is an equivalent one for radians. Instead of equaling 180 though, it equals pi. Right there.
Having flashbacks.
On the list of functions,
Yes, ma'am.
did you just not do the degree form for tangent?
Oh yeah, I missed the degree form. Sorry.
Okay, so the degree form is the same,
Yes. Thank you for pointing that out.
but the cotangent is not the degree, correct? Like the bottom one is not the degree.
So you just change this over to 90, 90.
This one.
Okay, sorry. Okay, Zach, fantastic point. You didn't necessarily remember the name, but that's not what I'm worried about. I'm worried about you remembering the math behind it. You're supposed to get 65 here because this angle is 25, this angle is 90. Add those together, subtract from 180, it should be 65. If that's the case, at this point in time, we now have two missing sides. This becomes a lot like last time and last week. We're trying to find the missing sides of a right triangle. You may, at this point in time, use either the 25 or the 65 as your main angle in the problem, your theta, because you have both. And that's also why this stuff works. Because take a look at this picture. Let's assume I want to use the 25 degree for everything. And I want to solve for A. Well, A is opposite of big A. So I could use A in the hypotenuse and do sine. I would do sine of 25 degrees equals A over 158 meters. The reason these formulas work is if I switch up to the other angle, I can use the same components, but I'd have to change trig functions. If I went up here and tried to do 65 instead, A is now adjacent to 65, so I'd have to use cosine of 65 equals A over 185. So we know these are, oh sorry, 158, my bad. So we know those two work because of the complementary function picture and because of this picture itself. Because when I use a different angle, I'm forced to adjust my sides to match to it. A is opposite of big A, is adjacent to this little phi. So if I switch the angle, I have to switch the trig function. That's why the complementary things work. Let's go back over here. We're going to solve this thing. I have this formula. I picked this formula because it uses one variable, A, and a known value, 158 meters. My goal now is to get A by itself. I'm going to multiply both sides by 158. It's starting to look a lot like last time. If you do not have a calculator, then this solution is acceptable, 158 sine of 25 degrees. If you do not have a calculator, that solution is acceptable. In your homework, it recommends giving them as decimal answers, so please do that as well. You get that for me, Zach?
Yeah, 66.774.
66.774. Thank you, man. Okay. Let's talk B. So again, this starts to feel a lot like last time. Once you get through the first growing pain of that, I need to put this into a picture. And again, I chose the picture to look this way as long as A is here and little a is across from it. As long as the missing angle is here and little b is across from that. As long as C is here and the C side is across from C. You can't draw the wrong picture. You may draw like the wrong size, but we don't care about the size. We care about the answers. And the answers come from the trig, and the trig doesn't change when we draw it a different way. Let's take a look. Now, in this case, let's do B. So again, I'm at this 25. That's my primary focus. So in this case, B would be adjacent to 25 degrees, and the hypotenuse would be 158. So I would use cosine of 25 degrees equals the B value over 158 meters. I think of B by itself, I'm multiplying both sides by 158. I did that 4 times that. 158. So if I don't have a calculator, B is equal to 158 cosine of 25. If I do have a calculator, I would convert that into a decimal form.
143.197.
143.197. Beautiful. Now, I had somebody, my last block, point out that I told you guys last time that you could use Pythagorean's theorem to check your work. And that is true. You can use Pythagorean's theorem to check your work. However, if you plug the decimal versions into Pythagorean's theorem, you will get an answer that's really close, not exactly the same. So like on this problem, if I did Pythagorean's theorem, I would on one side put the 158 squared. On the other side, I'd put the 66.774 squared plus 143.197 squared. This would be close. Like usually 1 or 2 decimals off, maybe even 100th or 1,000th off. It's close. It's real close. If you want to make sure they are exactly the same, instead you could put in these versions of the answers. If you put in the actual accurate version of the answer, Pythagorean's theorem works perfectly every time. Meaning, if you wanted to check this with Pythagorean's theorem, you'd have to type in 158 sine of 25 squared plus 158 cosine of 25 squared equals 158 squared. And this would give you an exact matching answer. Because of the decimals being a rounded version, they will always be close but never perfect. Those guaranteed will. Just make sure you put the entire thing in parentheses. Now again, you'll notice that between these problems and last time's problems, there's no major difference other than they do not give you the picture at the start. They ask you to interpret the information you're given to get a picture out of it. That basic format, big C being across from little c, big A being across from little a, big B being across from little b, that basic format will hold true for the rest of this semester and the rest of this year. So do note that fact and practice it for your tonight's homework assignment. Let's do another one. We'll do one more degree one, and then we'll do a radian one just to finish out to make sure we know the idea. Let's take a look. This time, what 2 pieces are we going to start with? Angle B is equal to 78 degrees. Side B is equal to 4.2 feet. All right, when given a problem like this in your homework assignment, priority number 1 is to convert this information into a standard picture. Now, what's standard about the picture is the location of the information, not the picture itself. You could draw the weirdest looking triangle you could do, and as long as the right angle is C, and one of your angles is big B, the other is big A, and the side across from big B is little b, and the side across from big A is little a, and the side across from big C is little c, it doesn't matter how you orientate this triangle, as long as you have that 6-part relationship with these 2 pieces put into it, you will never change the solutions for these problems. They can't change because otherwise math doesn't work, and that's annoying. Put them in. It says little b is 4.2 feet. It says angle B is 78 degrees. So it looks like I'm missing a couple things here. I'm missing little a, I'm missing little c, and I'm missing angle C. So 3 components I need to find. Maybe you guys a moment to try and get a head start in front of you. Okay? One of these can be found using the triangle angle sum theorem. The other 2 will require trig. I'll give you guys a head start and see what you guys think. This is very similar to last time. I want to hear what you guys know, and then we'll move forward. I don't have a calculator, so I can't check all of my work, but I'll get as close as I can. There are my 3 solutions circled in green. Angle A should be 12 using the triangle angle sum theorem.
What?
Did I go second?
Angle is 12.
12 degrees.
I got 13.
So I would do 78 degrees plus 90 degrees plus angle A equals 180. 78 plus 90 should be 168 degrees plus angle A equals 180. Yes, it should be 12. But always call that out if you think I'm wrong. I hate being wrong, so I'd rather check it. Okay? And then for little a, the side, I had to use tangent to find that one because tangent would involve using the opposite, which is 4.2, over the adjacent, which is a. So I can use those 2 components, and I ended up with a equals 4.2 over tangent of 78 degrees. That would put little a at can't do it. 0.893. Beautiful. Always check each other's work. Okay. And then for C, I had to use sine because the opposite of C would be B, and then the opposite of 78 would be the C. So we have the hypotenuse. So we end up with this equation in red. Multiply both sides by C, divide by sine of 78. I end up with 4.2 over sine of 78, which would end up being C as a value of 4.7. Somewhere in there?
4.294.
4.294. Oh, hold on. 4.294. And that would be in feet. The only difference is this is in degrees instead of in radians. Sorry, if this is in radians instead of degrees, would be we'd have to make sure our calculation's in the right form to make this work. And then the triangle angle sum would have to use a different formula, or you'd have to convert it into degrees through the formula. If the original problem is in radians, make sure your answer is in radians. If you want to convert in the middle, that's fine. Make sure you convert it back, though. That should be it for today. Tomorrow we'll go through 2 more definitions, and then we are done for the notes this week. The rest of the week will be spent on our quiz and on answering any questions from the homework that we want to get through. Yes, Anna, there is a quiz.
When?
Thursday. I didn't want to do it on Friday.
Andrew moved it all the way to Thursday. He's not even here.
I know, right? It's too bad. Alright, I'm going to stop the video.